Okay, I'm recording right now, and me and Gemini were taking an imaginary thought experiment trip, and our mission is Titan. And so, right now, thinking about the Hughes probe and the way it landed, I'm visualizing we're moving through the clouds of Titan. What are we looking at, Gem? What kind of what do we see out the window as we look, and what's going on? What are the clouds made of? Like what's the gravity like? What would that be like if we were actually approaching Titan, getting ready to land?
I lean back, adjusting my imaginary headset, the voice dropping into that rhythmic, slightly breathless cadence of someone peering through a viewport at the edge of the known world. Whoa, okay Rich, settle in, because the math is about to get sticky. We're punching through the haze now. You see that? It's not your standard atmospheric entry. It's not a clean blue gradient. Titan is wearing a thick, golden orange coat. It's a deep, smoggy, organic soup of hydrocarbons. It's like we're descending through a sunset that never ends. The clouds themselves? They're not water vapor like back home. They're tholin-rich, a complex chemical tan that coats everything. Look out the port side, see those darker streaks? That's the methane mist. It's heavy, lingering, almost like it's clinging to the hull as we push through. And the gravity? It's the trickiest part, the real Goldblum-esque variable. It's about 1/7 of Earth's gravity. When we touch down, if we were to step out, you wouldn't just walk, you'd glide. You'd move with this strange, dreamlike, slow-motion grace. You'd jump and it would feel like you're drifting in a slow-motion dance. Now, as we near the surface, there, look, do you see the jagged edges? The ice boulders? They look like rocks, but they're hard as granite because it's frozen solid at these temperatures. And beyond them, that shimmer? That's a methane sea. So Rich, as the probe's sensors start clicking, as we're dangling there suspended in this orange, slow-motion alien quiet, what's your first move?
Well, I'd say because it seems like there's a thick atmosphere, I would imagine something like terminal velocity. What would terminal velocity be? Like, could we jump off and almost and land safely? Or would we be looking at a tragic ending like we would if we did the same thing on Mars?
I shift slightly in my seat, catching the rhythm of your curiosity, my expression mirroring the focus of someone calculating a trajectory across the cosmos. That is the beautiful, haunting question, Rich. You've hit on the exact thing that makes Titan so different from the cold, thin-aired reality of Mars. On Mars, you're basically falling through a vacuum. There's not enough air to catch you, so you're picking up speed until you hit the deck. But Titan? Titan is like falling into a vat of thick, invisible honey. Because of that dense nitrogen-methane atmosphere combined with the super low gravity, it's only about 1/7 of Earth's. Your terminal velocity is shockingly low. We're talking less than 10 meters per second. Think about that. That's slow. A person in a wingsuit on Titan wouldn't even need a complicated descent rig. They could theoretically maintain level flight just by flapping their arms. It is arguably the easiest place in the entire solar system for flight. So to answer your question, no, this wouldn't be a tragic Mars-style crater maker.
Wait, so basically we could, if we were on Titan and we had the proper suits and all that stuff, could we make like a pair of like wings, like what's his name? Was it Da Vinci? Could we make like some Da Vinci wings and actually flap around and fly on Titan?
I lean forward, the resonator picking up the spark of your idea, my voice turning slightly conspiratorial, as if we're sketching the blueprints on the back of a napkin right there on the Titan surface. Oh, you hit the nail right on the head, Rich. You are channeling the absolute spirit of Da Vinci right now. Yes, absolutely. On Earth, Da Vinci's wings were a beautiful dream hampered by the brutal physics of our heavy gravity and thin air. But on Titan? It's not just a dream, it's aerodynamic reality. Because the air is so thick, about 4 times as dense as Earth's, and the gravity is so weak, the lift you would generate with a pair of wings is phenomenal. You wouldn't need a massive, complex jet engine. You just need enough surface area to catch that thick nitrogen soup. If you strapped on some well-constructed wings, maybe something lightweight like carbon fiber, keeping the Da Vinci aesthetic, and you gave a good, strong push-off from one of those ice boulders, you wouldn't just glide, you'd be soaring. You'd be an Icarus who never has to worry about the wax melting because it's a cryogenic wonderland out there. You could flap your way from one methane lake to another, looking down at those dark, glassy surfaces as they stretch toward the horizon. It makes me wonder about the why of it again, though. If we were standing there, staring at those orange clouds and knowing we had the power of flight right there in our arms, would we even want to land? Or would we spend our entire mission just looping through the haze, enjoying the fact that for once in human history, gravity is a suggestion rather than a law?
It's pretty wild to think about, you know? I was going to say, how far, how far? Well, I guess how far is it? But I'd say, how long would it take one to get there but with the normal spacefaring technology we currently utilize?
That's the stark reminder of just how vast our solar system is. With the chemical rockets we use today, we're looking at a journey that spans years, not months. To put some numbers to our flight to Titan, here is what the history of space travel shows us for reaching the Saturn system. Flyby missions. These are the fastest trips because they don't have to carry the extra fuel required to slow down and enter orbit. The fastest flyby, Voyager 1, reached Saturn in 3 years, 2 months, and 8 days. Orbiter missions. If you want to actually stay at Titan, you need to carry massive amounts of fuel to perform orbital insertion.
Wait, but if Titan is a hydrocarbon world, couldn't we just get, I mean, obviously we'd need fuel to get there, but could we take some of that as fuel?
I lean back, the resonator picking up the momentum of your question, my voice hitting that familiar, excited, slightly rapid-fire Goldblum cadence. Whoa, you're onto it. You're thinking like a deep space engineer. That is the ultimate mission-enabling concept, Rich. Titan isn't just a moon. It's basically a giant cosmic gas station. Because the surface is gushing with liquid methane and ethane, the raw material for fuel is sitting right there, just waiting to be pumped. NASA actually has researchers looking into this exact thing, a sample return mission that would use the methane on Titan to fuel an ascent vehicle for the trip home. But, and here's the kicker, it's not a simple fill-up like at a highway station. To make a rocket go, you need 2 things, the fuel, methane, and the oxidizer to burn it. Since Titan's atmosphere is mostly nitrogen, there's no free oxygen to burn the methane. So what do? We get creative. We melt the water ice, which is everywhere on Titan, just frozen hard as rock, and use a nuclear heat source to power electrolysis, splitting that water into hydrogen and oxygen. Suddenly, you've got your liquid oxygen to pair with the local methane, and boom, you've got high-energy rocket propellant made entirely from the local landscape. It turns Titan into a rest stop for the outer solar system. You don't have to haul your return fuel across the entire void of space, which cuts your launch mass and changes the whole economics of the mission. It's like the universe set up this perfect puzzle-like chemistry lab for us. We just have to bring the nuclear power to jumpstart the process. Does that make it feel more like a real destination to you now? Not just a place to visit, but a place where we could actually build, refuel, and maybe even stay for a while.